Means, medians, modes, variances, and standard deviations. It's time to take a look at measures of central tendency and variability. This is Totally Doable Stats. So as we take a look at these measures of standard deviation and variance, what we're trying to figure out is exactly how much variability there is in a set of data we're dealing with. And so what we're going to do to figure this out the best is actually compare between two data sets. And so let's start with what we'll just call data set X. And we'll make that, let's go with 10, 15, 20, 25, and 30. And then we'll do a different color and go with a different data set. We'll use data set Y. And this we will make 16, 18, 20, 22, and 24. Well, the first thing we want to do is really find out what the mean is of each of our data sets. And so if you'll remember from last time, this formula for mean is going to be the sum of all of my values divided by the number of values that I have. So for this first one, I'm going to have 10 plus 15 plus 20 plus 25 plus 30, all divided by 5, which is going to equal, let's see, that's 25, that's 50, so 25 and 25 is 50 and another 50 is 100 divided by 5. My mean is 20, which you can kind of tell by looking at it, right? And so data set Y, and let's go with a little bit different color so you can really tell them apart. We're going to have 16 plus 18 plus 20 plus 22 plus 24, all divided by 5 again, which again is going to equal 20 by the time we get all done. And so if we're going to go through and think about these data sets, the mean is a number that represents each of these data sets, and we can see these are the same, but they're clearly different data sets. And so we need another way to talk about these data sets to be able to really understand the differences between them, and that's where measures of variability come into play. Last time we talked about measures of central tendency. Here we're going to talk about and compare variability in these sets. And so one of the things we're really looking for in order to understand variability is something called deviation from the mean. That's really what we're looking at for how much variation there is. We want to know how much deviation there is from the mean in each of these data sets, and then a way to think about that more carefully. So let's bring up another page here. And again, we'll remember data set Y was not starting with 22, was it? Data set Y was 16, 18, 20, 22, and 24. And that is the value of Y, all the different possible values of Y in the data set. And if I'm looking at data set X, well then my values were what? We had 10, 15, 20, 25, and 30. And for each of them, the mean was 20, right? So if I'm going to calculate the deviation from the mean, deviation from the mean is simply going to be whatever the individual score is minus the mean, and always in that order, which means up here if I have x minus m and I do a column of that, then I'm going to have 10 minus 20 which is minus 10. 15 minus 20 is minus 5. 20 minus 20 is 0. 25 minus 20 is 5. And 30 minus 20 is 10. Likewise, over here with my y column, if I do y minus m for these, then 16 minus 20 is negative 4. 18 minus 20 is negative 2. 20 minus 20 is still 0. 22 minus 20 is 2. And 24 minus 20 is 4. Now to think about, so we can see the variation of each of the data points. But if I want to talk about the variation of the entire set, then what I really want to do is figure out some kind of average deviation, right? What is the average deviation across the entire data set? That'd be a good piece of information to know. The problem is when I go to actually try to calculate the average, if I add up, you can see it here, if I try to add up negative 4 and negative 2 and 0 and 2 and 4, well, these are going to cancel each other out, and these are going to cancel each other out, which leaves me with a 0. I can't really do anything with an average if I have a 0, so I have to figure out some way to get rid of that 0, some way to get rid of those negative numbers. And in math, there are really two ways to go about doing that. One of them will be to take the absolute value of each of those, but what we're actually going to do is square them all. So we're going to create a new column, and we're going to square each of those deviations. So negative 4 squared is 16. Negative 2 squared is 4. 0 squared is 0. 2 squared is 4. 4 squared is 16. Again, if I do the same thing over in my original data set and data set X, negative 10 squared is 100. Negative 5 squared is 25. 0 squared is 0. 5 squared is 25, and 10 squared is 100. And so now that I have all of the squared deviations, I can add those up and take an average of what the squared deviations are. And that is actually going to give me my variance. The symbol for variance is sigma squared, and that's how I'm going to figure out my variance. It is the sum of all the squared deviations divided by however many I've got, and that's how I'm going to figure it out for a population. And so when I go to figure that out, let me erase that, get that out of the way. If that's my formula, I'm going to have 100 plus 25 plus 0 plus 25 plus 100, all divided by 5, which means I'm going to have a variance of, let's see, 125 plus 125 is 250 over 5. So that's going to be 250 divided by 5 is 50, is going to be my variance. And the other side here, I'm going to have, if I add them all up, it is going to be 16 plus 4 plus 0 plus 4 plus 16, all divided by 5, which gives me a variance of 20 and 20 is 40 divided by 5, that's 8. Now the variance is a useful piece of information, and it'll become much more useful later in the semester with a specific statistic we're going to talk about called the ANOVA. But most of the time, if I want to know an average kind of deviation, well, the variance, I'm still dealing with all those squared numbers. So I need to unsquare it to see something that looks like an average deviation. And instead of calling that an average deviation, we're actually going to call that a standard deviation. And to calculate it, it's just exactly like I said. We are going to unsquare the variance. And so we'll represent that with a sigma, and it just equals the square root of the variance, which in this case, over on this side, is the square root of 8. which you may understand is the square root of 4 times 2, right? And so I can actually take the square root of that 4. In this instance, the standard deviation is 2 times the square root of 2. Back on the first data set, I'm looking at sigma being the square root of 50, which is kind of like the square root of 25 times 2, right? And I can take the square root of that 25, so it's 5 times the square root of 2. And so notice, when we're looking at what our average deviation is, you can see this one is by a factor of 5 compared to this one being at a factor of 2. And we can actually see that in the data set, where this one was by a factor of 2, and this one was by a factor of 5. That was a horrible 2, and it's not even the right color. So let's try that again. 2. And so we can actually see with these really easy number data sets, we can actually see what that represents and understand that we're describing the variability a little bit. That means we can go beyond just that one simple number representing the mean and also talk about spread, exactly how the data varies within the set. And that ends up being useful information when we're doing our analysis. Hopefully, as we've computed these, you've found that they're not that hard. They're actually fairly easy, which is why we call these totally doable stats.